Thank you everyone for joining us today, and welcome to GOWIN's webinar series. Today's presentation will be going over GOWIN's family of I3C IP products. My name is Andrew Deuteronic with GOWIN, and I'll be your moderator. Please feel free to send us questions via the question or chat button throughout the presentation. We'll answer those at the end of the webinar during our Q&A session. Rajeev, our Senior Field Application Engineer, will be our presenter today. Now for a brief overview of GOWIN Semiconductor. GOWIN was founded in 2014 and our executive headquarters is located in San Jose, California. Our operational headquarters is located in Guangdong, China. We have over 160 people employed in R&D, engineering, and administration. We serve the low to mid-range density markets for FPGA needs, from 1,000 LETs to 100,000 LETs. For more information about GOWIN Semiconductor and our latest innovative products, please visit us at gowinsemi.com. At this time, I would like to start our main presentation.
Hello everyone, welcome to today's GOWIN I3C webinar. My name is Rajeev, a senior FAE based in San Jose, California. I support customers who are in the eastern United States and in Canada. Today, first I'll be talking about I3C, about 30 to 35 minutes. And then after the presentation, there will be an I3C demo showing basic I3C writes, reads, and interrupt operations between an I3C master, or a controller as it is called now, and 3 I3C targets, or the slaves. After the demo, there will be a Q&A session. If you have any questions along the way, please type it in the Q&A window. I'll try to answer as many questions as possible within the hour. In case we run out of time, the answers to all unanswered questions will be emailed to everyone who are in the webinar today. Any questions so far? Let's move along. Before we dig deeper into the I3C interface details, let me tell you what I3C is and how it is related to the decades-old I2C interface, or I2C interface as we know it. The I3C interface incorporates key attributes of the traditional I2C and SPI interfaces to provide a unified, high-performing, very low-power solution. It also delivers a robust, flexible upgrade path for I2C and SPI implementers to I3C. Today I'll start with a quick recap of I2C. Then I'll move on to I3C and compare the two I2C and I3C interfaces and show you how similar they are and where they differ. Then I'll discuss the I3C bus protocol as it relates to the start, stop, and interrupt conditions on the bus. Next, I'll discuss the advantages of moving from I2C and SPI to I3C. Then I'll present 3 GOWIN I3C IPs and discuss their main features. Next, I'll show you how you can configure and instantiate an I3C IP from GOWIN in your design using the IP code generator in the GOWIN EDA tool. That will be followed by a demo of GOWIN I3C IP. And lastly, I'll be answering your questions in the Q&A session before concluding this webinar. A little bit of history. NXP, through its Philips legacy, has owned the I2C specifications. The I2C specification has been around since the mid-1980s. That's as far back as I can remember. And the I2C interface has been actively used in many designs, even today. According to a 2013 MIPI survey, about 90% of the sensors used in operation then used I2C as their primary interface. That's a lot of sockets. The I2C has been used mostly to transfer data collected by sensors to the CPU, to configure sensor devices, and also as a control bus to send commands, among other applications. Here is a simplified block diagram of the main I2C components, the I2C master and I2C slave on a 2-wire bus, a clock and data, with resistor pull-ups on both clock and data lines. So the bus operates in an open collector or open drain configuration. The frequency of operation of this bus is typically 200 kilohertz to 400 kilohertz. In other words, it's a very slow bus. There are some special cases with special IOs you can operate up to 1 megahertz, but that is very rare. It is used typically for low bandwidth applications such as peripheral configuration, sensor data, and few other applications. You can actually cook up an I2C interface using C or Python code by bit banging two GPIO pins. From the 1980s, fast forward about 3 decades and we come to I3C. So what is I3C? Around 2013, NXP along with Intel and Qualcomm came together with a proposal to upgrade and improve the I2C specification. This is done to meet the growing bandwidth demand for sensors for the IoT age. Towards the end of 2016, the first draft of I3C specifications was released, and since then, a lot more companies around the world have jumped on the I3C bandwagon. Although the I3C started out as a sensor interface, it has found use in many other applications, not just sensors alone. In 2013, an I3C Alliance was created under the MIPI umbrella by NXP, Intel, and Qualcomm as the founding members. MIPI is the Mobile Industry Processor Interface, the standard setting body for mobile phones. The goal of this alliance was to come up with a specification for the I3C interface, and more importantly, it was to be made available to the members of the I3C Alliance for use without any royalties. Under the MIPI umbrella, several versions of I3C specifications have been released. The latest adopted version is I3C 1.1. I3C is backward compatible to legacy I2C standards. In other words, an I3C master will support the I2C slaves. An I3C slave can operate in the legacy I2C environment controlled by an I2C master. GOWIN Semiconductor is a MIPI Alliance member, and we have implemented all mandatory features of I3C 1.1 standard. I3C stands for Improved Inter-IC Communication Bus. Unlike I2C or I2C as it was called, with 3 I's, this is just called I3C and not I3C Bus. It is a successor to I2C Bus, and it's built on I2C protocols, which we'll discuss later in future slides. Here there are only 2 wires, just like in I2C, the SCL, the clock line, and the STA, the data line. There is only one pull-up on the data line and no pull-up on the clock line. Unlike I2C, the STA line on I3C bus operates in open collector or open drain mode only during the address or the bus arbitration phase of the transaction. It then switches to push-pull mode during the data phase of the transaction. It is this operating in push-pull mode allows for higher transfer rates. Like in I2C transaction, a read-write is always initiated by the I3C master or the controller, and the I3C slaves responding to the request. On an I3C bus, you can connect an I2C slave device and it will work just as it did on an I2C bus with some caveats. Also, an I3C slave in an I2C bus will power up as an I2C slave device and will continue to work as so. The I3C started off as a sensor bus, but it has now found its use in lots of other applications. Here are a few. Memory sideband channel in DDR5 applications, always-on imaging, server system management, test and debug applications, touchscreen command and control, power management. Let's look at the I3C bus protocol. When there is no transaction on the bus, both the STA and SCL lines are pulled to their high or the inactive state. A start condition on the bus is when the SCL is high and the STA line is going from a high to a low level. Conversely, the stop condition on the bus is with SCL being high and the STA line going from a low to a high level. Then a restart condition is very similar to the start condition, that is with SCL being high and the STA going from high to a low level. So this is just as it was in the I2C standard, absolutely no change here. In I3C, there is no separate interrupt line for the I3C slave. The interrupt lines are embedded in the STA and SCL lines. Here is how it goes. When an I3C target or the slave wants to interrupt the processor, it does so by pulling the STA line low when the bus is idle. It then starts emitting its slave address. There could be multiple slaves or targets wanting to interrupt the CPU, and they all are emitting their addresses on the STA line at the same time. The I3C slave with the lowest address wins out the arbitration and receives the ACK from the I3C master. The I3C slave then can put out one or more bytes on the STA line for the CPU to service the interrupt accordingly. This is all good, but why would you need to use I3C interface in your design? What are its advantages and benefits? We will discuss these in next few slides. On a typical mobile phone these days, there are different kind of sensors to measure distance, light, temperature, brightness, and pressure. These sensors are getting smaller and their performance is increasing stronger with every release of the next model of the phone. A stronger performance translates to higher requirements in data rates and lower power consumption. All the sensors are typically handled by an applications processor. First on the left is a typical sensor hub application processor that aggregates data from various sensors and sends it upstream. Depending on the sensor, there will be one or two interrupt lines to the processor while using an I2C bus. In short, this is a very messy connection, and not to mention the lower data rates and higher power consumption. Let's see how the same sensors on an I3C bus look like. A very clean two-wire connection to the CPU operating at much higher speeds with interrupts embedded in SCL and STA lines and at much lower power consumption. Here are some raw performance numbers for I3C. The SCL clock light can go as high as 12.5 MHz in operation. In I3C, it is the I3C master or the controller that generates and sends the clock when initiating a read or a write transaction on the I3C bus. So when the data transfer happens on every rising edge of the clock, the transfer rate works out to 12.5 megabits per second. This is called the standard data rate, or SDR. The data can also be transferred on both edges, the rising edge as well as the falling edge of the clock. In this mode, the data rate is doubled to 25 megabits per second. This is called double data rate, or the DDR mode. There are several optional modes called the ternary modes, TSL, TSP, which are too complex and they increase the size of the IP considerably. Due to patent issues, they do include payment of royalties. For this reason, these optional modes have not been implemented in our IP. As mentioned earlier, there are no separate interrupt lines in I3C. They are built into the I3C protocol. When a slave wants to interrupt on I3C, it pulls the STA line low when SCL is high. When it is granted the use of the bus, it can put out a single or multiple bytes for the CPU to service the interrupt. Lastly, the I3C specification has something called the CCCs, or the common command codes. They are similar to command codes in SM bus. With 0x7e as the address, the I3C master can broadcast commands to all slaves to set some register to a particular value, or direct a single I3C slave to respond to a command on the bus. Here is a side-by-side comparison of an I2C and an I3C transaction. They are pretty much alike for a typical read or a write operation. For both, the bus idle condition is when both SCL and STA lines are high. Since it's always the master that is initiating a transaction on the I3C or I2C bus, it is the one that is pulling the STA line low. That is followed by 7 bits of slave address for both I2C and I3C, and the 8-bit determines whether it is a read or a write operation. An address slave, if present on the bus, responds with an ACK on the bus. This is followed by a data phase in which I2C or I3C master writes 8 bits of data to the slave on every rising edge of the clock. In case of write in I2C, the 9th bit is called the ACK bit, in which the I2C slave responds with an ACK indicating that it has received the data. In case of read in I2C, the master responds with an ACK to the slave that has transmitted the data. In case of I3C, during the 9th bit, it is called the T bit, where a parity of the data that has been just transmitted either by slave or by the master for each other to compare and check for errors. In the middle of a transaction, the master can do a read or a write operation to another slave on the bus by pulling the STA line low when SCL is high and sending a new slave address on STA. This is called a repeated start condition, which is really a start condition. The data transfer follows as described earlier. For a write operation, the ACK-NACK response is from the slave, and for a read operation, the ACK-NACK response is from the master, that is in I2C. Here is a visual comparison of power consumption and data rate numbers for I2C and I3C devices. On the left is the energy/power consumption chart. Here you can see that the I3C devices consume way less power than their I2C counterparts. It is because the actual data transfer happens in push-pull mode for the I3C devices, whereas the I2C devices are operating in open drain mode all the time, resulting in higher power consumption. As far as the data rate is concerned, there is no comparison. 25 megabits per second for I3C versus 400 kilobits per second for I2C. What does a typical I3C subsystem look like, and how different is it from an I2C subsystem? Let's examine. Let's go back to the sensor hub that we discussed in earlier slide. The data is gathered from all the sensors in the system, processed by the application processor, and then sent to the main CPU upstream. One thing to note is that the I3C is a multi-master environment, but at any given time there can be only one master on the I3C bus. Typically, there is a designated main I3C master that's normally controlling the I3C bus. The main I3C master initiates read-write operations on the I3C bus. It also acknowledges the interrupts by I3C slaves on the bus and then sends the interrupt bytes to the CPU for servicing the interrupt. However, there can be one or more secondary masters on the I3C bus that are normally operating as slaves but are I3C master capable. These secondary masters can issue master request and be granted the bus mastership by the main I3C master. The secondary master finishes the data transfers that it wants to do and returns the bus mastership to the main master. Or the main master at any time can take back the control of the I3C bus by requesting the bus mastership. In the subsystem, there are just plain I3C slave only devices that are connected to the I3C bus as shown above. And the legacy I2C devices on the I3C bus that need a separate interrupt line to the application processor can also be present. There is only a single pull-up resistor on the STA line of this I3C subsystem. Now let's focus on GOWIN's I3C IP offerings. In the GOWIN EDA tool, when you open up the IP code generator, you will find three different flavors of I3C IPs. I3C Master Slave Combo IP, I3C Master Only IP, and I3C Slave Only IP. Since I3C is a multi-master environment, generally an I3C master in the system should be I3C slave capable. That is the reason why we have the I3C Master Slave Combo IP, but there might be a closed application where there are no secondary masters. In such circumstances, only the I3C master functionality is needed. So we have the I3C Master Only IP. The interfaces to a sensor do not need any master capability, so we have the I3C Slave Only IP. Let's go over these IPs one by one. The first of the GOWIN I3C IPs we'll be discussing today is the I3C Single Clock Master Slave Combo IP. This IP is compliant to I3C 1.1 version of the specification. This happens to be the latest one that has been adopted by MIPI. Here is a simplified port diagram of the IP. It has a single clock FCLK into the IP, and all other clocks including SCL are derived from this clock. We have implemented all the mandatory features of I3C 1.1 specification. They include the SDR mode and DDR modes of operation. We have achieved 12.5 megabit speed for single data rate mode and 25 megabit speed in double data rate modes of operation. This IP supports address arbitration for all the I3C slaves, where an I3C slave with the smallest 7-bit address is the winner. The IP does the dynamic address assignment for all the I3C slaves on the bus. We support in-band interrupts and hot join. When an I3C slave joins the bus via hot join, it is allocated a new dynamic address. Our IP can reset a stuck I3C slave on the bus by emitting a reset pattern. This IP is backward compatible to I2C, meaning that an I2C slave will work on an I3C bus, but the interrupts will have to be dealt directly by the application processor. We support two interfaces, an APB interface to connect to a sensor hub, or a simple register-based interface to connect to a single sensor. The maximum frequency of operation of this IP is determined by the device used and the speed grade chosen. When the system clock is 100 MHz, the SCL for this IP can go up to 12.5 MHz. The resource utilization may vary with different devices or the speed grades. A typical LUT utilization for this IP is about 2.2K, and the register usage is about 1.2K. The next of the GOWIN I3C IPs we will be discussing today is the I3C Dual Clock Master Only IP. Like the single clock version, this IP is also compliant to MIPI I3C 1.0 version of the spec. Let's look at the simplified port diagram of the IP. In addition to the FCLK into the IP, we have another clock called I3C_CLK. The FCLK is slow and is used to do the register read and write operations. And the I3C_CLK is fast and it is used to generate SCL and can go up to 100 MHz. The ratio of I3C CLK to FCLK must be 2:3 for normal I3C communications. As for the features, we have implemented all the mandatory features of I3C 1.1 spec. They include 12.5 megabit speed at single data rate mode and 25 megabit speed at double data rate mode of operation. Like the single clock version of this IP, we support dynamic address assignment DAA, in-band interrupts IBI, hot join, and we also support slave reset to reset any stuck slave on the I3C bus. APB interface or simple register-based interface is provided to connect to sensors. In this IP, SCL depends on the frequency of I3C underscore CLK pin. When I3C CLK is 100 megahertz, the SCL can go up to 12.5 megahertz. The LUT utilization for this IP is about 1.9K and the register usage is about 1.1K, which is slightly less compared to the single clock version of this IP. The last of the GOWIN I3C IPs we will be discussing today is the I3C dual clock slave only IP. This IP is pretty much the I3C dual clock master slave combo IP with master functionality disabled in it. Since this is a dual clock IP, we have two clocks, FCLK and I3C underscore CLK going into the IP. The ratio of I3C underscore CLK to FCLK must be 9:4 for normal I3C communication. There are no changes on how these clocks are used. FCLK is used for read and writes and I3C underscore CLK is used for generating SCL clock on the I3C bus. Feature-wise, the I3C dual clock slave only IP is compliant to MIPI I3C 1.1 specification. We have achieved speeds up to 12.5 megabits per second in single data rate mode of operation and speeds up to 25 megabits per second in double data rate mode. Features such as dynamic address assignment, in-band interrupt, hot join, and slave reset are supported in this IP. We also provide choice of APB interface or a simple register-based interface to connect to your sensors. When the I3C underscore CLK is 90 megahertz, the I3C SCL speeds up to 12.5 megahertz. The LUT utilization for this IP is about 1.K and the register usage is about 1.05K. This is slightly less compared to the I3C dual clock master slave combo IP. In the next couple of slides, I will show you how you can configure and use these GOWIN I3C IPs in your design. Before I do that, I would like to mention that all the IPs from GOWIN, including the 3 IPs we discussed today, are provided to you for free and contained in the IP code generator of the GOWIN EDA tool. You will require no additional license or need to pay any royalties for use of these IPs in your design. First thing you'll be doing is making sure that you pick the right device in terms of the resources, that is number of LUTs and registers. Keep in mind that these GOWIN I3C IPs utilize about 2.2K LUTs and 1.5K registers. Make sure you account for these resources when you choose the FPGA for your design. Next, start the IP code generator from the Tools menu or by clicking the icon for the IP code generator as shown. Then select Softcore, Interface and Interconnect I3C Single Clock IP. A configuration window with title I3C Single Clock IP will pop up with a couple of parameters for you to choose and generate the IP. Depending on your application, you may choose a register interface if you have a single sensor or an APB interface if you have a sensor hub connected to an APB subsystem. Keep the disable I/O insertion selected as this is done at the PNR stage by the tool. Choose OK to generate the IP. The IP code generates all the necessary files for synthesis and gives you an IP instantiation template to be included in your design. The steps to generate the I3C dual clock I3C master slave combo IP is very similar to the steps mentioned in the previous slide for the I3C single clock IP. When it comes to choosing the IP, choose the I3C dual clock IP. Then a window pops up just like the one for the single clock IP. Here choose the IP interface to be either APB or register depending on your sensor type and click OK to generate the IP. Then use the instantiation template and make the connections in your design. The steps to generate the I3C dual clock slave only IP is very similar to the steps mentioned in the previous 2 slides. When it comes to choosing the IP, just choose the I3C dual clock slave only IP to configure. I'll skip this and move on to the next part of the webinar. This completes the first part of today's webinar. Next, I will move on to the demonstration of GOWIN I3C IP working with a third-party I3C IP. First, I will explain the demo setup and then perform basic I3C operations such as writing data to a register, reading it back from the register and verifying that the data was written correctly, execute a global common command code getBCR, and then perform an in-band interrupt IVI operation. Here is the GOWIN I3C demo setup. It has three main components: a PC or a laptop with application that can send I3C commands via USB UART, which is FTDI based. Second, a microcontroller that receives I3C commands from the PC on a UART port and then decodes them to create instructions to I3C master that is connected to it. Third, GOWIN I3C dual clock slave only IP that is connected to the I3C master via the I3C bus. The I3C bus in this demonstration is implemented on the brown and yellow fly wires that are connected between I3C master board and the I3C slave board. There is a 1K pull-up resistor on the STA line of the I3C master board that is controlled internally by the I3C master. This resistor is turned on during the bus idle and the address phase of the I3C transaction and turned off during the data transfer phase so that the IOs operate in push-pull mode at much faster rate. After connecting the USB UART from PC to the I3C master board, power up the I3C master and slave boards. Wait for the FPGAs on both boards to finish configuring and run the application on the PC. The next thing to do would be to configure the I3C master by writing to the master configuration register. The I3C clock frequency SCL is determined by the value set for PP baud, PP low, OD baud parameters as shown in the configuration window. After the I3C master is configured, the I3C application is ready to send I3C commands to the microcontroller connected to it. On power up, the GOWIN I3C is powered up in I2C mode with the slave address of 0x56. The first thing to do is to program the starting dynamic address to I3C master using the setD commands by writing the value in the box provided next to the setD button. Here we have 0x2E written in the box, and you will see an acknowledgement saying that 0x2E is written when the button is pressed. The next thing to do is to instruct the I3C master to go out on the I3C bus and configure all I3C slaves connected using the ENTDAA command. When EDAA button is pressed, the I3C master finds GOWIN I3C slave and configures it with the dynamic slave address of 0x2E. After programming, the GOWIN I3C slave responds with its capabilities, that is, slave only, HDR capable with single byte IBI support. It also responds with the manufacturer's ID and some additional information about itself for the I3C master to use. After the I3C slave configuration, it is ready to accept commands from the I3C master. The first command we will send is to write to the register at location 4 a data of 0xA5 by using the WI3C command. When WI3C button is pressed, you will see that data 0xA5 is written to the register at location 04. This can be verified by reading 1 byte from location 0x4 using the WR3C command. Here we read back 0xA5 from the location. Let's repeat the write and read operation with data 0x7A. So as expected, we have read back what we wrote, which is data 7A at location 04. Next, let's move on to the global common command codes, or the CCCs. Get BCR is a GCC from I3C master to an I3C slave, which directs it to respond with its value in its BCR register. So when GCC 0x80 is executed, the I3C slave returns 6 bytes as shown. The SIPI command accepts IBI requests from the current slave and displays the IBI byte received from I3C slave as shown. In this case, the byte received from GOWIN I3C slave is 0x56. This concludes the I3C demo of GOWIN I3C IP. Some of you may have stumbled upon I3C recently, or may have heard about I3C or know about it but are not sure if I3C is the right interface for you in your upcoming projects. If you would like a one-on-one consultation, please find a link to the form in the chat window, fill it out, and we will schedule a time with you to go over the details and answer any questions you may have. Now I will open up the Q&A session. As mentioned at the start, I will answer as many questions as I can within the hour. Any unanswered questions will be answered via email and sent to everyone in the webinar.
All right, thank you, Rajeev. So the first question we have here is, why have we not implemented the ternary modes such as TSL, TSP in our IP?
Right, good question. These ternary modes, they are patented by a large IP company that shall remain nameless, and they enforce their patents rigorously. So there's royalty involved in that. That is one of the reasons. In addition to that, it requires more logic and special IOs, so it cannot be implemented using standard GPIO type IOs. So those are the main reasons, and plus there's not been much interest from our customers asking for these ternary modes. But if any of you need these, let us know. We will work on that. It'll take some time to implement, but we can do it.
Okay. Next up, we have I3C 1.1 supports multi-lane SDA, but I only see single-lane SDA in our IP. Why is that?
That also sort of is similar. The answer is similar to the one I just said. For most of the sensor type applications, single lane at 25 megabits per second is good enough. Of course, there are some applications where we might need higher speed, so we'll have to go to multi-lane. But so far, our customers haven't asked for this, so that's the reason why we haven't done the multi-lane option. It's again also this is an optional feature. It's not a mandatory feature, but if anyone requires it, let us know. It's fairly easy to extend from single lane to multiple lanes.
Okay, thank you.
All right.
Next question I have is, just like in I2C, you can stretch SCL if the slave is not ready with the data. Can you do that with I3C?
No. Actually, the cycle stretching is not part of the I3C spec. However, some vendors have implemented cycle stretching. We have not. Again, it's an optional feature. So we have not implemented cycle stretching in I3C.
Got it. Next up, we have, what is the resistor value of the pull-up resistor on SDA?
So SDA resistors, typical 1.1K should do. 1 to 1.K is standard recommended by MIPI.
Got it. Next, we have, can you talk about I3C hot join?
Good question. I did mention about hot join briefly in one of the features. So the hot join feature is
while the I3C is in operation, a slave, according to the MIPI spec, can join the bus. So that's called hot join while the bus is in operation. So when that happens, the master detects that, and it configures the newly slaved I3C with a dynamic address, and then figures out its capabilities, and then allows it to operate like other slaves which were brought up during power up. So it's a fairly it's in the spec, and we have implemented this thing, and we have tested it, and it works. So hot join is a feature in all of our IPs.
Got it. Next question I have for you is, can I use little b with 4K LUT?
With 4K LUTs, it might be a little tight depending on your design. So this alone takes about 2K LUTs, so that's 50% of it already gone. So probably it'd be a good idea if you move to the 9K device.
Makes sense. Up next, we have, do you have any control, status, or debug registers?
Control and status registers are part of the MIPI I3C spec, so we have them implemented. Not sure exactly what debug registers mean. I know I3C used to have like a scratchpad register. I'm not sure if you're talking about that. But we have implemented all the mandatory control and status registers of the MIPI spec.
Got it. And I have another one here, the GW2AR18 embedded in this IP Tang Nano 20K. Is that compatible with I3C technology?
Yes, indeed. So the GW2AR18 has plenty of LUTs available, with I3C occupying about 2K LUTs. This would be a perfect device for using I3C. And it's got standard GPIOs that should work without any issues. In fact, on one of our demo boards, we have implemented that in a GW2AR18.
All right, looks like that's all for our questions. Thank you everyone for participating in today's webinar. A recorded video of this presentation will be available by tomorrow, and you'll be sent a link directly to the email you used to register. This concludes the webinar. Thank you, stay safe, and have a great one.